Afternoon, everybody. It is a pleasure this afternoon to have as host our speaker, Sriram Bhiravarasu. I hope that I spell it right. Let me briefly introduce our guest. Sriram got his PhD in physics on planetary sciences from the Gujarat University in India in 2016. Afterwards, he moved at the Arecibo Observatory in US from 2017 till 2018, working on radar observations of near-Earth asteroids, comets, terrestrial planets, and moon. Later, Sriram moved at Lunar and Planetary Institute at Houston, Texas, again US, working on the analysis of LRO data. And since 2020 is staff scientist at the Space Applications Center at ISRO in Ahmedabad, India, working on both Chandrayaan-2 DFSR data acquisition and analysis, and also polarimetric and radar scattering of moon and terrestrial planets. Today, Sriram will talk about water ice at the lunar poles, a radar perspective. Thanks again, Sriram, for accepting our invitation. You have 45 minutes. I'll inform you when you have 5 minutes left.
Yeah. Thank you, Mike, for the kind introduction. Let me share my screen first.
Sure.
I hope you can see it.
Not yet.
Okay, let me
Now
turn off my off my video so that I can save some bandwidth.
Okay. We can't see your screen yet.
Yeah. So it is it visible now?
We don't see your screen yet. Okay, now it's going to go. Sure. It is working.
Okay. Yeah, so good afternoon, everyone there at INF. This talk is it's a kind of overview of how we detect the water ice on planetary surfaces, and then the special emphasis today is on at the lunar poles, because most of you might have seen in the news sometime that the presence of ice being reported from different wavelength observations. So today's talk is based on how the radar detects or even interacts with water ice. This is the outline of my talk. So radar is a very useful remote sensing tool for studying the planetary geology, because it is sensitive to composition in terms of the dielectric properties, the near surface structure, and then the roughness of the surface at the wavelength scale. So I will introduce a bit of radar jargon and then jump into the detecting water ice using radar, like all the techniques and some prior results from ground-based radar studies. And then I will talk about the lunar poles, how they appear in radar images. And then my last topic will be a comparison of the poles of Mercury and Moon, because they are very much similar, but their radar characteristics are quite different. And then where we stand now in terms of the detection of ice from lunar poles, and some way forward, like what we are presently doing and what the radar community is presently doing in terms of pursuing this objective. So let's start with the radar in general. So typically what we do is radar is an active instrument. It operates in the centimeter wavelength scale, typically from 1 centimeter to 100 centimeters. So it is sensitive to particles of sizes of 1/10 up to 10 times the wavelength we use. And then in dry geologic environments, it can penetrate up to 10 times of the wavelength used. So typically radar measurements use all aspects of the electromagnetic waves, including the frequency, the amplitude, and then the polarization of the received waves to understand the target surface. The cartoon on the left is a very classic uh, figure which shows the effect of radar geometry while studying the surfaces. You can see the radar incidence angle. That means the angle of the radar waves that makes with the surface plays a very important role in understanding the received radar echoes. You can see from the curve that when the surface is smooth at very low incidence angles, the surface acts like a mirror. You will have a very high backscatter from such smooth surfaces, whereas from when the surface gets typically rough in the sense of the wavelength we use, it is generally not so affected by the incidence angle employed. And then there is one important parameter which I need to describe here, because we will be talking about this parameter throughout my talk, which is the circular polarization ratio. That means you transmit a circularly polarized wave and then receive in two different senses of polarization. That means both the same sense and then the opposite sense of what you have transmitted. So for example, if you transmit a left circular polarized wave, then you receive both left circular as well as right circular polarizations, and then you make a ratio out of it, which is known as the circular polarization ratio. So this is a first cut indicator of several parameters, including roughness as well as detection of ice in certain conditions. So the cartoon in the middle shows how the interactions of the radar waves with the target surface gives rise to these two different polarizations, where you have the OC, the opposite sense, is dominated by single bounce reflections. That means mirror-like reflections from the surface, either from the undulating surface or from the scatterers such as rocks present on the surface. Whereas the same sense returns are enhanced by reflections taking twice. That means typically from a regolith to a rock or vice versa. And radar always sees a volume, so we cannot assume that it is just coming from the surface, but it typically sees 10 times of the wavelength, but that depth is governed by the dielectric properties of the top surface. So CPR is a very sensitive indicator of the near surface roughness, and the figure on the extreme right shows the typical CPR values encountered from planetary surfaces. So when you have a smooth surface, the CPR is very much less than 1. And when the surface starts getting rough, from smooth to moderate to very blocky surfaces, this parameter rises. So in some situations, the CPR also crosses the value of 1. So again, to um, emphasize the advantage of radar, it provides complementary informations of subsurface, which is a unique perspective compared to other wavelength measurements such as the optical and near infrared. And then it provides a unique perspective by which we can explore several geologic processes and their influence on regolith development on dry geological surfaces, including the detection of volatiles such as water ice. So what are the radars available now for exploring the lunar surface? So we have a typical ground-based radars available for us since the 60s. I have shown an example here. This is a place where I have worked. This is the Arecibo radar facility. Unfortunately, it got damaged in 2020, but till then, it was the world's largest planetary radar facility. It has a diameter of 305 meters. So it can transmit circular polarization and then receive in both senses. So the first orbital radars for the moon are the MINISAR and the MINI-RF, flown on Chandrayaan 1 and LRO missions respectively. So what they do is they typically transmit circular polarization, but they receive in linear polarization. So it's a kind of different technology has been used in order to balance the mass requirements on a planetary mission. So these two kind of radar instruments are form of a compact polarimetry. That means we transmit one polarization and then receive in two different polarizations. Now, the one on the extreme right is the DFSR instrument, that is the dual frequency synthetic aperture radar on the Chandrayaan 2 mission, currently which I am part of this science team. So this is the first ever fully polarimetric radar instrument sent out for a planetary mission. This operates in both L and S bands. So when I say L band, it is around 24 centimeter, and then when S band, it is around 12.6 centimeters. It has several different modes of polarizations in both transmission as well as reception. So the important thing to note here is all these radar instruments can generate the CPR parameter, which I have just described in the previous slide. And so this is all the radar instruments, all the measurements boil down to this slide. If I can put this into a perspective of detecting water ice from radar. So the most accepted physical principle in detecting the ice is through scattering from the thick layers of ice. The theory behind this detection is called the coherent backscatter opposition effect. In classical physics, this is also called as weak localization theory or time reversal symmetry. So what happens is when a radar wave enters a thick sheet of ice, several wavelengths thick sheet of ice, a constructive interference between this radar signal happens between the radar waves that travel in the same path but in opposite directions, and then these signals are forward scattered, which preserves the original sense of polarization. So which gives you a huge increase in the intensity of the received waves, as well as it preserves the polarization. So what happens is this preserves the original sense of polarization that has been sent. In this case, we call it as the same sense polarization. So since CPR is a ratio of same sense to the opposite sense, we will have very high values of this CPR parameter along with radar brightness measurements. So the theoretical prediction says that this phenomenon is most effective with closely spaced wavelength size scatterers of low refractive index. Typically, this happens when you have a few wavelengths sheet of ice with voids present in between the ice. So that acts as a perfect surface for this CBOE to happen. So this was done in labs on a gold surface, assuming it as a perfect scatterer. So they kind of uh, measured this peak at zero phase angle. So this is the theoretical background to detect the ice from radar observations. The cartoon on the right shows the different CPR ranges that we observe from a rough surface when compared to a surface which has a sheet of ice, because forward scattering in such icy environments preserves the polarization and gives these high values of the CPR. But there is a caveat that This high CPR can also be explained by extremely blocky surfaces, such as blocky lava flows we typically encounter on Earth, because these blocks on geological surfaces acts as double bounce reflectors, because they form this perfect double bounce geometry from the surface and these kind of blocky material. This also causes CPR values of above 1. I have shown some examples here from both terrestrial and lunar features where we encounter such kind of blocky surfaces. This is a image of SP crater flow in Arizona. This is a blocky andesitic lava flow. And then on the right, you have lunar examples. This is the Tycho crater on the top, which is a very young crater with all its ejecta distributed around the crater. And then couple of other two craters which were detected in radar images having such blocky flows, impact melts, having these kind of very high CPR values. So a little bit of context here, that ice is not only detected or being detected or pursued on the lunar poles, but we have a very rich background of such radar observations from other icy surfaces in the solar system, that is the Galilean satellites. These were carried out in the 70s as well as the 90s from the ground-based Arecibo radar system. As you can see, all these icy Galilean satellites have this parameter circular polarization ratio very much higher than 1. These are the two papers which I have shown here, highlights these observations. And the figure in the center compares all these icy surfaces with typical dry surfaces such as the moon. As you can see that the Europa, Ganymede, and Callisto, they have very high circular polarization values as well as very high radar brightness. So the parameter on the y-axis is the total power, which is the radar albedo or brightness, and you can see the values for Europa. The figure on the right, which is a very recent result, which have been examined again, shows the typical values of these CPR parameter compared for Europa versus the moon. So the gray line here is for the moon, and you can see the stark contrast between these icy Galilean satellites and the moon, as well as Mars and Mercury polar features, which you can see from the middle image. So the takeaway is that for these icy Galilean satellites, there is no evidence of specular reflection at wavelengths ranging from X band up to P band. So X band is typically at 3 centimeters, and then P band is the longest wavelength used for planetary radar observations. So what these authors have observed is that all these radar echoes coming from these icy Galilean satellites are because of multiple scattering through these thick layers of ice. So let's start with the topic of water ice with a bit of background here. So the evidence of ice on the moon, it started with this seminal work of Watson in the 60s. This is a theoretical work which first predicted that water ice can exist at the lunar poles in some regions of permanent darkness, which we now refer to them as permanently shadowed regions, because sunlight has never reached those regions at the poles because of its tilt with the ecliptic plane. So some regions at the lunar poles are under perennial darkness from billions of years, and these theoretical studies in the 60s predicted that ice could exist in such regions. And three equally important components to the delivery and trapping of these ice particles is their sources. That means they could be either exogenic or endogenic. Exogenic in the sense that they could be delivered from, let's say, comets or other icy asteroids during their impacts. And endogenic processes are because of the end products of volcanism. And then once they are delivered to the surface of the moon, the transport process of these water or ice to the polar regions, and then how they are stored from these billions of years. So all these things play a very important role in determining the exact location as well as the abundance of water ice when we deal with the radar. Now, on the right, I have shown the exploration of lunar PSRs, that is the permanently shadowed regions, right from 60s, where you have theoretical predictions, and then from 90s, we have these actual observations of lunar poles that were started from lunar missions. The first is the Clementine bistatic radar in 1996, and then we have a lunar prospector mission. And in the early 2000s, there are Earth-based experiments using radar. And then from 2009 and 10, we know that there is a huge uptick in the lunar missions from several nations, including the US, Japan, India, China, and also the ESA. So the table on the right shows the kind of sensitivity we obtain from different wavelength measurements when we are targeting these PSRs. So you can see that starting from the ultraviolet to passive microwave, what are the typical depths that can be sensed by these observations, as well as the detection limits. So when we see the radar in this table, we can see that it can sense up to 10 meters down the regolith, and it can only detect macroscopic blocks. That means if it is present in the form of uh, sheets or blocks, then radar can detect through the process of scattering, and the underlying phenomenon is the coherent backscatter opposition effect, which I have just described previously. So let's start with the Clementine bistatic experiment, because this is the start of all the radar experiments we have till date. So Clementine, they had a radar on board the Clementine spacecraft. What they did was they transmitted from the radar. They pointed out to the lunar poles, and then it was received from the ground stations. That means the ground radar observations situated at different locations, which was operated by NASA. So this bistatic radar experiment, this measured the magnitude and polarization of the radar echoes versus the bistatic angle. So bistatic angle in radar is just analogous to the phase angle in optical observations. That means the angle between the instrument, the receiver, and the surface. So what they observed was very high elevated CPR values in the south polar region at this bistatic angle close to 0. So they predicted that this could be an indication of presence of patchy ice deposits in the permanently shadowed regions located in the Shackleton crater. So Shackleton crater is located exactly near the lunar south pole. The rim of this crater has that 90-degree south point. However, several later studies using the same data again, uh, meaning that reanalysis of this data, indicated that several ambiguities are still present regarding the validity of these claims. So even though the first cut results showed that the spikes they have observed could be because of ice, but later studies revealed that this ambiguity cannot be resolved. And then after the 90s, two experiments in the early 2000s, 2003 and 2006, using the Arecibo Radar Observatory at Puerto Rico. were performed at both S band as well as P band. That means at 12 centimeter and 70 centimeter. So they transmitted from Arecibo, pointed at the lunar south pole, and then received at the Green Bank telescope, which is situated in West Virginia in the US. So they observed at a close to zero bistatic angle, very much similar to the Clementine bistatic experiment. So these results were both of these results were appeared in Nature in 2003 and 6 respectively. So what they observed was the spikes observed in the CPR parameter in both S and P band radar data are correlated with the surface roughness. That means the inner and outer parts of these craters, because of their elevated surface roughness, is giving rise to these high CPR observations. That means they clearly pointed out that whatever we are observing from radar brightness as well as the CPR is not due to the presence of ice, but it is due to the presence of surface roughness associated with these craters present near the South Pole. And then after 2006, with the launch of Chandrayaan-1 as well as the LRO, we have MINISAR and MINIAR radars orbiting from the spacecraft. And then these two results in 2010 and 2015, which showed the mosaics of both poles in S band, predicted some anomalous craters, which actually coincided with the permanently shadowed regions. And they observed that the high CPR values, along with the local geology, as well as matching with other wavelength observations such as the low epithermal neutron flux, as well as the seasonal temperatures, they predicted that all these anomalous features observed in these mini RF polar images, this could be due to the presence of ice. So this again stirred up the story that what we are actually seeing with radar could be water ice, but not roughness. So this was in 2010 and 2015. But several studies later, using this same mini RF radar data. So I have shown some examples here. There are actually so many studies, but I picked 3 of them. I was also part of a study in which we modeled radar albedos of lab characterized particles and then applied to lunar surface. So all these results pointed out that there is no difference in the CPR values with the potentially icy surfaces and non-icy, not non-polar craters. That means the CPR we are observing in these polar regions is again due to roughness, as well as we also could observe that the same phenomenon is occurring in the non shadowed regions also. And our modeling approach proved that the ice particles are indistinguishable from the regolith unless we can be very certain that ice plays a major role in the shape of the particles. So we performed some numerical simulations, taking the size, shapes, and the different dielectric constant values, and then showed that unless this ice occupies a significant part of the typical radar pixel, we cannot be sure that all these high CPR values are because of the presence of ice, but mostly it could be due to elevated roughness in those regions. Now, another interesting twist in the story is the Cabeus crater and the L-cross impact. So LRO mission had this experiment in which they dropped a Centaur rocket into the lunar South Pole region. So it crashed into a region on the floor of Cabeus crater, and using another shepherding spacecraft, they measured the plume and discovered several volatiles, including the presence of hydrogen, hydroxyl, as well as water. So the mini RF team at the time used these both Chandrayaan 1 and LRO radars, and then observed the Cabeus surface both before the impact, before the L-crash impact, and as well as after this L-crash impact. And you can see from the curves on the bottom left that there is no difference, practically no difference between these shadowed regions and non-shadowed regions in both Chandrayaan 1 and LRO. And the CPR values are typically less than 0.5, indicating that the surface is very degraded and there is no such presence of ice, at least that can be detected by radar. The one on the right is a result I have presented in LPSC couple of years back. We obtained new L-band radar observations of from the DFSR instrument on board Chandrayaan 2, and what we have observed is that even though the CPR values are very much correlated with the earlier observations, so using this polarimetric data, we calculated two other parameters, that is the dielectric constant as well as the surface roughness of these patches inside the Cabeus crater. And then we observed some patches on the floor of Cabeus, which could say that they could contain some patches of water ice mixed with the regolith, but there is no presence of thick deposits of pure water ice, at least within a few meters of the regolith, up to where this L-band radar can penetrate. So we did not rule out the presence of small discrete pieces of ice mixed with the regolith, but as we know, as this roughness plays a very dominant role in the received radar returns, we could not exactly separate those patches from the surface, but the mixture, the values of dielectric and the roughness pointed out that there could be some patches of water ice on the floor of Cabeus. So taking the story forward, there is a different category of observations called bistatic radar, which was done using Clementine. And then in the early 90s, this very famous lab experiment was carried out, in which they observed the radar observations of polystyrene spheres in a water, which is kind of analog to ice. So what they observed is they observed this scattering from this polystyrene spheres as a function of the phase angle. So as you can see on the figure on the right, you can see a sudden spike when you reach the 0-degree phase angle. So if you can study this radar observations as a function of phase angle, that means the bistatic angle, then you can very confidently say that what you can observe, what you are observing is example of water ice, but not your typical average regolith. So the figure on the bottom right is again an example to show that the ice analog is clearly separated from other materials. So in this experiment, they used surface of a silicate glass to separate out these measurements. So you can see that these two typical curves are far separated, and the response of the silicate glass is very flat compared to these polystyrene spheres. So this is again a prediction of the coherent backscatter model for the unusual radar observations of icy satellites, which predicted the presence of ice. So again, by using these lab-based experiments, these showed the importance of the bistatic angle in detecting the ice and then separating it from roughness. So one such experiment was carried out using mini RF on board the LRO. A radar wave was transmitted from Arecibo to the Cabeus crater, and then it was recorded on board this LRO using mini RF. So the figure on the extreme left is again the CBOE theory, where when you observe these radar waves as a function of bistatic angle, it can clearly separate the ice and rocks using the circular polarization ratio, which peaks near the zero bistatic angle. So you need to observe the surfaces at a range of bistatic angles in order to separate this presence of ice vis-a-vis the rocks. So the figure in the middle summarizes all these observations so far carried out for Cabeus. It shows the monostatic ground-based observations as well as the monostatic mini-SAR and mini-RF observations, as well as the DFSAR observations. It shows the CPR ranges observed from these, as well as the curves, which shows the bistatic mini-RF observations of Cabeus, and you can clearly see the opposition effect when the bistatic angle reaches near zero. So this predicted a kind of opposition surge, which is matching with the theoretical predictions of water ice from the Cabeus crater floor. But several questions remain in this interpretation because the same observations carried out from ground as well as from spacecraft does not have such kind of opposition surges at zero bistatic angle. So this is still an open issue, that why only bistatic observations have predicted water ice in the Cabeus and not the monostatic observations carried out using ground-based as well as spacecraft-based radars. So this is the final concluding part of my talk. This is a comparison of two polar surfaces, Mercury and the Moon, because both the bodies are very similar in size and the same dry environment, as well as the polar environment is quite similar because they have almost the same axial tilt from its normal surface normal. So both the surfaces have permanently shadowed regions. So several studies of Mercury poles carried out using ground-based Arecibo predicted the presence of water ice. On the figure in the top left, this is the Arecibo radar image of Mercury South Pole. This is from the 2012 Arecibo observations. And all the bright patches you are seeing are actually the regions of thick water ice. And the plot on the bottom, it shows the comparison of Mercury poles with other icy satellites in the solar system, and also the average Mercury surface. So the red dot on the bottom is the average CPR value of the Mercury surface, whereas the Mercury poles, as you can see, that they have very high SC albedos, giving rise to CPR values of above 1, and they almost compare with the icy Galilean satellites as well as Europa, which is the highest, which has the highest enhancements from radar observations. So I was part of a study of Mercury poles carried out in 2019. This was a paper published in 22. We observed the Mercury's North Pole deposit, and then when we plotted these kind of observations, so the figure on the right clearly separates the polar bright deposits from the average background terrain all the blue points are the high radar albedo features from these permanently shadowed regions, clearly indicating the presence of ice, whereas all these black points, which are formed in the form of a cone, they are the background terrain data. And the one on the bottom is the same curve carried out for the moon. So you can see that all these points are overlapped. The polar anomalous as well as young as well as non-polar features, there is no clear separation between these. So these stark questions remain because both have same conditions of temperatures and illuminating conditions. But there is a stunning contrast in the radar properties of these polar deposits on Mercury and the Moon. So the most important question now is why the volatile concentrations at the Moon and Mercury are very different when you observe with the radar. So this is the status quo of lunar water ice. So we definitely know that there are no large patches of water ice on the near the lunar poles, but if it is present, it should be present in the form of dirty ice that is mixed with the regolith. So ice could be dirty, or it could be present at depths beyond the penetration of currently available radar observations. And then when you compare the Mercury versus Moon polar environments, regions of less pure ice within the Mercury's PSRs have been detected. And interestingly, they have CPR values of less than 1, but still they contain water ice. So this could also happen on the Moon, but we still don't know. When in terms of bistatic observations, only the Cabeus floor has shown a positive response, and but somehow it's not comparable with monostatic results. So two typical scenarios for detecting water ice from the lunar environment are shown on the right here. So on the left, if let's assume a surface where you have a few centimeter top of regolith on top of thick multiple wavelength thick sheets of ice. So theoretical prediction says that the ice layer should be at least 100 times the wavelength of observation. In this scenario, we can detect the presence of ice using the coherent backscatter opposition effect. Or if the ice occupies a typical radar pixel, I mean more than 50% of radar pixel, then it can be detected on using any wavelength. So these are some of the modeling results presented in 2011 paper. And so what we are currently doing, or what is lacking, are realistic scattering models to understand the radar return from the lunar terrain. So we are currently targeting 3 different kind of scenarios where the regolith contains ice inclusions, that is the dirty ice scenario. And then when the ice is buried beneath the regolith, because then you have to understand the thermophysical properties of both the top layer as well as the buried ice. And then another interesting and important phenomenon is what happens when the ice includes a significant volume fraction of rocks. So these are the 3 current modeling scenarios we are targeting. And then when you compare with Mercury, some regions of water ice have been observed with these CPR values of less than 1. So we are targeting those kind of regions where you have these CPR less than 1 values using new radar data, especially the DFSR, which I'm currently working on. And then comparing with other wavelength observations such as the thermal infrared as well as neutron data. And yeah, we need more bistatic observations. We just have Cabeus from mini-RF. So we have a plan to transmit from DFSR hit the moon and then record at any ground-based observatory. So we are contacting a few radar observatories to do this task. But it is a very huge experiment because we need to coordinate with several teams. But bistatic observations will give a clear-cut indication of ice versus roughness. So these two figures at the bottom are some of the predictions of theoretical modeling, where you have a range of CPRs observed when you have no rocks. That means though if the surface has only ice along with silicate grains, as well as when you have rocks with different kinds of volume fractions. This is an example from a 2011 modeling paper. So we are currently working on these kind of theoretical modeling efforts, and if anyone listening to this are interested, I welcome for discussions, as well as if you are interested to participate or collaborate, I welcome all of you. I will stop here and then take any questions. These are the beautiful polar maps we have generated so far using DFSR data on Chandrayaan 2.
Okay, thanks, Sriram. And let me. Okay, we have a question from Piero here. Let me interrupt the registration first.